My name is Ian Todd. I'm from BBC Sky Night Magazine, and I'm here at the International Astronomy Show 2022. And I'm here with Professor Nial Tanvir from the University of Leicester. It's a bit busy out in the show itself, so we've sort of gone backstage to nab a quiet room and talk about the early universe and re-ionisation and all sorts of amazing things like Redshift, and that you've been talking about at the show today.
Yeah.
I was hoping, it might be cool just to sort of go back to the very start of the story. How much do we actually know about the early universe and what it was like after the Big Bang, and how soon after the Big Bang can we pick up the story?
Okay, so it's an interesting question because, oddly, the sort of very early universe, the first second, the minutes of the universe, we believe we understand pretty well, despite the fact that we can't actually see in any direct way that very early time. And the reason is really that the universe was in some sense very simple then. It was just a soup. And we can therefore, of all the particles that exist in nature, and therefore we can just use the physics that we know pertains to those particles and the forces between them to calculate what the conditions must have been like. And we can use that to trace with a lot of confidence back to very early times. Oddly, it then becomes more difficult. As we wind the story forward, we have a sort of good benchmark at around about 400,000 years, because something happened there, which was the release of what's called the microwave background radiation. This was the radiation of the hot Big Bang. It suddenly found that it could go through the universe unimpeded, because at that moment, the electrons that had been kicking around in this plasma rejoined with the protons in particular to make neutral hydrogen atoms, and the other atoms became neutral as well that were around. And so suddenly those photons spread through the universe, and we can still see them today. So that gives us a very good sort of fingerprint of what the universe was like then. And then again, you've got a mysterious period, what we call actually the Dark Ages, when the universe, we think we probably understand, was just expanding and cooling, but something else must have been going on. It must have started to collapse the gas into the beginnings of what we would now call galaxies and stars, etc. And so that Dark Ages period is very hard to study directly, and so is that early phase of the star and galaxy formation. Later on, of course, then we start to get into the regime of the universe that we really can study, pardon me, with Hubble and the rest. So, then after that, it becomes pretty well established.
Is some of that process you described, is that what we term ionisation, the epoch of re-ionisation?
Right. So when those early stars and galaxies turned on, it seems that around about that time, or shortly thereafter, all of the gas that still existed between the galaxies, of which there was a lot, went from being neutral, that we think came out of the Big Bang eventually once it cooled, became neutral. Then at some stage it became ionized. In other words, the electrons were ripped out of their atoms again, and you again had a hot plasma existing between the galaxies. And we assume that happened by high energy radiation being produced by those first stars that were created in the universe. If that can spread out, and you need quite a lot of it, but if it can spread out through the gas between the galaxies, then maybe it can do that job. Something's done it. So, that's the puzzle, really. What has done it?
Yeah. And what sort of observations and observatories and telescopes enable us to effectively see back in time?
Yeah, well, so a number of different. The nice thing is, in many ways, about modern astronomy is that we can use light across the electromagnetic spectrum to get different sort of angles in on any problem or any period that we're interested in. And so on the one hand, we might use more regular optical telescopes, or actually you have to sort of nudge into the infrared, just sort of the slightly redder light than the optical, in order to see galaxies at these sorts of distances, at these high redshifts that we're talking about. But observatories, particularly like the Hubble and now JWST, have really geared up for doing that. Coming at it from another way, we can, for example, use radio telescopes looking at that microwave background radiation. We said that was produced a lot earlier, but that also interacts with some of the gas later on around the period of reionization. And so that gives us another way in. in the future, we're hoping to use a different kind of radio telescope to directly detect the neutral gas that was still around. So I'm telling you, it's started neutral, ended up ionized. There has to be a sort of process going on between the two. And the newer radio telescopes that are now being built and working on trying to detect the signal of that sort of change of state from neutral to ionized.
You mentioned Redshift there, and that featured really heavily in your talk.
Yeah.
And that's a pretty mind-blowing concept in itself. Can you give us an overview of Redshift?
Yeah, so it's Redshift is interesting, of course, the discovery that the galaxies that we see around us in the universe, all the features in their spectra all seem to be moved to the red end of the spectrum compared to where we would expect them to be. So these are features created by particular atoms, particular elements in whatever it is that's produced the light, or sometimes the gas that's sitting between us and the light source, imprints either dark absorption lines or sometimes bright emission lines on the spectra. And so you know where you expect those to be, what wavelengths. You find them at another wavelength. They've all systematically moved apparently to the red end of the spectrum. We interpret that in terms of a velocity. It seems that practically every other galaxy in the universe is moving away from us with some fairly high velocity. And it turned out, and this was the big discovery really made by Edwin Hubble back in the 1920s, was that the further away you look, the faster everything is receding. And so that was the discovery of the expanding universe. Hugely profound discovery in its own right, but also a jolly useful tool for those of us that are interested in mapping the universe and exploring its history and its evolution, because we can tell by measuring the redshift, which is something we can do, we can tell how far away the objects are, we can tell how far back in time we're looking, and therefore you can look at those key moments in the history of the universe that way.
Incredible. So is that what Hubble used to sort of determine that there are other galaxies?
Yes. Well, so he'd already, what Hubble's real work was, and this is Edwin Hubble, the astronomer, was to, for the first time, actually measure distances to other galaxies, which is actually surprisingly hard to do. Space is big, real big. And so measuring distances to other galaxies, it had been a sort of controversial issue for, the early decades of the 20th century. Hubble came along in the 1920s and measured those distances. He was fortunate enough to be around at a time when other people were actually measuring the velocities that I've mentioned. And he kind of gets credit because he put the two together, realized that all the galaxies he measured to be nearby to us were not moving very fast away from us. The galaxies that he measured to be more distant were moving faster away. And hence, you make a big name for yourself when you make that sort of discovery.
Absolutely. So when we're when astronomers are peering back to the early universe, have we pieced together a sort of decisive picture as to how those first stars formed and then how the first galaxies formed? Can we piece all that together?
No. This is very much still stuff at the frontier, you would say, compared to what the situation was like 20, 30 years ago, when it was really you were peering really into the sort of distant realms, and we really didn't have a lot to go on. Things have certainly advanced a lot. We certainly now see an era of what must be the early galaxy formation, but the processes that gave rise to those first stars and galaxies are still enshrouded in quite a lot of mystery. And I'll give you some indication of why. One is that the stars themselves, we know quite well, of course, we observe stars forming all around us, so we've studied those processes pretty well over many decades. And one thing that requires, obviously it requires a cloud of gas to start contracting and to become quite small and to fall under gravity until it makes something as dense as a star, and then it switches on. And it turns out that whole process goes much better and more efficiently if there are already heavier chemical elements within your gas cloud, and maybe other factors as well, like magnetic fields can have an influence. All of those things would not have been around in the early universe, and the very first stars that must have formed couldn't have formed in the same way as the stars around us. And so that's something that's still largely studied by kind of simulations, by people trying to sort of think how gas would behave under those sort of circumstances. And I think it's still the case that, we're really lacking direct observational evidence. And of course, these stars are going to be really hard to see, even with JWST. I mean, exploding stars might be one of the ways that you can actually see them. So that's one of our hopes, is that we can begin maybe in the next few years to start finding very early first generation stars as they explode rather than as they live, because maybe they're just too faint to see. And similarly with the early galaxies, you've got again the question of how the gas actually collapses to make those early galaxies. It's easy to sort of hand wave and say that it must have happened, and it clearly did happen. But how it happens, it gets complicated. It's not easy to simulate. It's easy enough to simulate the behavior, for instance, of dark matter in the universe. But as soon as you talk about normal baryonic matter, it starts to do complicated things. It falls, it warms up, some of it ionizes. It's altogether a more complicated process. And so again, we're kind of very much looking at the new data that are coming in now from the telescopes like James Webb just recently, like the ALMA telescope, etc. These sorts of new facilities that start to picture to put that picture together, really.
Okay. Let's move actually on to gamma ray bursts.
Yep.
Am I right in thinking that that's your particular area?
That's my
specialties?
particular thing. Yeah.
So, what is a gamma ray burst? Do we know specifically what they are and what causes them?
Right. So they're an interesting class of objects or of events, partly because actually there's more than one way of producing them, but I'll focus on the one that's most relevant to what we're talking about. And that is that we know that many gamma ray bursts, in fact, the brightest ones, are produced by massive stars. Massive stars are, of course, short-lived. So we're talking about a star that's maybe 30, 40 times the mass of the sun when it was born. Doesn't live very long because it burns out its fuel very quickly. Once that happens, the star on a very short time scale collapses, and the center of the star, which was altogether more dense in the first place, collapses very quickly, a fraction of a second, whilst the rest of the star is collapsing in at a more leisurely rate. Now, what we think happens, and there's a fair amount of evidence in support of this picture, but it's not totally concrete, is that the center of the star, if it's spinning very fast, probably that central core forms a black hole. Material falls very quickly into that black hole, and in the process, it releases a lot of energy in that collapse process. That energy seems to come out in the form of very, very high-speed jets of material. Exactly how those are accelerated is still also not fully known, but they clearly come out, bursting out of the star now at something like 99.999% of the speed of light, so extraordinarily fast. Huge amount of energy in them, and it is the radiation produced within those jets that gets emitted as gamma rays that we see then as a flash of gamma rays with our satellites, and that's your gamma ray burst.
It sounds like they're very chaotic, but also very fast, transient events.
Yeah.
So how do you catch one in action?
Yeah, it's not easy. I mean, of course, in one sense, it's easy because one of the nice things about gamma ray detectors that we have on these telescopes, these satellites, is that they see a large patch of the sky typically at one time. And so in a sense, they just stare, and every now and again a flash will go off in their field of view. And so then they've seen it. The problem is they typically don't give you very good localization. They don't tell you much else about it. They don't tell you the redshift. They don't tell you anything about the host galaxy, any of those things. They just say, there's a flash over there. So we find we have to use lots of other techniques to hone in, decide exactly where that flash came from, look for what we call the afterglow of the gamma ray burst, which lasts a lot longer than that original flash of gamma rays. That is what we then use to give us the redshift, the host galaxy, learn about the properties of the host galaxy and all these interesting things.
There was a really interesting bit during your talk where you were explaining that you sort of have you're on high alert, and sometimes it happens at night.
Of course,
so you're actually just woken up at 2 a.m.
Yes.
There's a gamma ray burst?
Yes, SMS messages. So when we first started doing this with gamma ray bursts, it just coincided with when text messaging first appeared on mobile phones, and it was kind of convenient because typically that's exactly what you want, is a short message will wake you up. You'll then bleary-eyed look at your computer, find out a bit more about it, and if it looks like one that merits further follow-up, then you crawl out of bed and and do the necessary business, as it were. Yeah. Mm.
What do you do if you're like on holiday or like staying at a hotel?
Oh, yeah.
Well, you're at a wedding or something.
Of course, ideally, you try and put teams of people together.
Yeah.
So hopefully we usually have teams. It's hard to keep people that kind of maintain their enthusiasm for this over many years.
I can imagine.
But there are always a few old timers that are still prepared to do it, as well as at least a few younger folk for whom it's all still novel and exciting. And so, yeah, between us and of course, you get into the routine of it. We have various bits of software that make it a bit easier, but there's no doubt it's probably not very healthy. Probably my GP would say I should stop doing it, but
But I mean, it's obviously worth it. So what do we get from studying gamma ray bursts in terms of the wider universe? Can it tell us something about the wider cosmos?
Yeah, in a very interesting way. So it gives us a sort of completely different window, if you like, on the distant universe. It's because essentially they're so bright and the light actually is so pure as well. And it means they're almost a sort of perfect beacon to look at if you want to study the gas that's on your line of sight to the gamma ray burst. So the afterglow in particular, if you can get a spectrum of that, you see all sorts of features in it, all of which are produced by gas along the line of sight, material along the line of sight. And so that means that we can look at these very distant, sometimes extraordinarily faint galaxies that cannot even be seen by JWST or the Hubble in very deep exposures. So these are galaxies that are, to all intents and purposes, invisible, but a gamma ray burst went off, we got a spectrum, and it means we can tell how much hydrogen gas was there, how much of the other kinds of elements, and all of that ties into if you've got any other elements you see there, those elements must have been produced by the early stars in those galaxies and spat out into that host galaxy interstellar medium. So, we're kind of learning detailed things about these early galaxies, which would otherwise just be mysterious. That's
so cool. And, at the time of recording, we sort of had about 3 or 4 months, I would say, of James Webb Space Telescope data and images, and the Square Kilometre Array organization is sort of due to come online.
Right.
What about these new observatories? Are you looking forward to using them in terms of your research? And will you get gamma ray burst observing time on James Webb, for example?
It's a fine question, and you'd hope that the problem with James Webb is that of course, it's a very very expensive and in-demand kind of facility. So all the different areas of astronomy are trying to get their slice of it. The other problem for us in particular is that it's not really geared to making fast observations. So we certainly expect to observe the host galaxies of gamma ray bursts, and we already have programs that have been awarded time to do that. And so that's something we hope to use James Webb successfully to do. We haven't actually got any observations yet, so I can't give you any results there. The other thing we do hope to do is, at least for some very special gamma ray bursts, perhaps the highest redshift ones, or conversely, the other very interesting topic is ones associated with gravitational wave events. In those cases, I think there's a very strong case for James Webb to point its spectrographs at those events, and I think almost certainly it will do, albeit it's a difficult. The other thing about James Webb is that it can't just point anywhere on the sky at any given time. So you could just be unlucky. The most important event of the decade might happen over there, and it might just be simply not in James Webb's region of sky that it can observe at that moment. And so, if that's the case, then you lose out. But that's the nature of this game. It's a game where we can't really always predict. We write telescope proposals knowing full well that the most important thing we might do with the time is not something we've written in the proposal, because exciting things happen in this game that you can sort of guess at, but you just don't know what's going to come up.
Yeah. Could you sort of conceive any actual dedicated space telescope mission dedicated specifically to studying gamma ray bursts?
Yes. There are already ones that exist. that find the gamma ray bursts and localize them. What we don't have are ones that really do the detailed follow-up observations, and that's something that we've had the ambition to build for a long period of time. Various concepts have been constructed and studied and proposed to various space agencies with more, greater or lesser degrees of success. It's unfortunately the case. Of course, all these things are very expensive. You're always in competition with, many other plans that people have, other satellites they want to build. And they also, particularly if you want to build a very ambitious and capable one, have a very long lead time. So even if you get funding now, it's going to be, maybe late 2030s before it actually sees the light of day, as it were. What I can tell you is, in fact, even just next year, there is a new Chinese-French satellite, actually, that Leicester University happens to have a part in, that's going to be launched, which does have rather more capable follow-up onboard telescopes than has been the case in the past. So we're making some progress. That will be, if you like, the next step forward, but isn't quite what we want in the sense of, our real ambition would be to have a fairly big infrared telescope and spectrograph on board the same satellite that detected the gamma ray bursts. And so that's something that we're hoping will get funded. We have, there are plans that are being reviewed at the moment by the European Space Agency, for example, and so fingers crossed that might be funded.
Yeah, absolutely. And good luck with analysing whatever this French Chinese
yes, thanks.
Happens to observe. Thanks for taking the time to speak to me at the show, and thanks for coming on the podcast.
It's a pleasure, of course.